Welcome to Chapter 1, Operating System Theory. In today's lecture, we're going to talk about the basic operating system concepts, and we're going to give you a short history of operating system development. We're going to discuss how operating systems work. In specific, we're going to talk about the types of operating systems, and we're going to discuss the difference between single-tasking operating systems versus multitasking operating systems. And while we're talking about single-tasking versus multitasking, it's an opportune time to also discuss a little bit between single-user and multi-user operating systems. Lastly, we're going to list and briefly describe the current operating systems that are in use today and considered popular. So let's go ahead and get started. Before we can talk about operating systems, you need to have a definition of an operating system. For this course, we'll define an operating system as a set of basic programming instructions to computer hardware, forming a layer of programming code on which most other functions of the computer are built. Think about a computer as being a layered device, with hardware and hardware instructions or firmware encoded instructions at the hardware layer, the operating system sandwiched in between, which serves as a liaison with the hardware, to the third layer, which we call applications. But we'll talk more about that later. The kernel is the programming code that is the core of the operating system. And when we talk about code, we're usually saying generally that that is a set of instructions written in a computer programming language. We refer to that as code. The kernel, by definition then, is the core component of that operating system. The part of the operating system that if you took it away, the operating system would no longer be an operating system. Now, computer hardware consists of the physical devices such as the CPU, circuit boards, the monitor, keyboard, disk drives. Things that we attach to the computer are hardware as well, but we refer to those as peripherals, like printers and scanners. Now, for the sake of this course, there are two types of operating systems that we will cover in this book. Desktop operating systems, which are installed on a personal computer or PC and is used typically by one person at a time and may or may not be connected to a network. Examples of installations are desktop computers, laptops, even iMac computers are all examples of desktop operating systems. A server operating system is installed typically on a more powerful computer that is connected to a network and typically enables multiple users to access information such as email, files, or applications. Now, examples of hardware with a server operating system would include traditional server hardware, rack-mounted server hardware, and the blade servers that you hear so much about today. When we refer to a traditional server, this is typically a server that you'll see in a small or medium-sized business. It usually consists of a CPU box, which we refer to as a freestanding CPU box. It has a keyboard and a mouse just like a desktop, and sometimes even a monitor, though it's not required. A rack-mounted server can typically hold multiple servers, and all servers often share one monitor in a rack and a pointing device, a mouse in other words. Rack-mounted servers you oftentimes see in medium to large size businesses, which typically require multiple hardware installations to run multiple types of applications or multiple functions within the institution. And even larger organizations or in companies that provide hosting for servers, you often see blade servers. Blade servers typically look like a card that fits into a blade enclosure. Each card represents its own physical hardware device or server. A blade enclosure is nothing more than a large box with slots for these blade servers to be installed in. And typically, like I said before, you see these in medium and large organizations because you can run so many servers and because of the cost of the unit. So, what is an operating system tasked with? Well, a basic task of an operating system is, quite honestly, to take care of input-output functions. This lets other programs communicate with the computer hardware. So, when we talk about input-output tasks, what are we referring to? Well, we're talking about input from the keyboard, the mouse, and other input devices. We're talking about output to the monitor and printer. We can also handle remote communications if we have a modem or network card installed. And we also have input-output for devices such as a network interface card, control information and storage retrieval using different types of storage mediums, oftentimes disks. And we also enable multimedia use for voice and video composition, which would be input, or reproduction, such as a recording video from a camera or playing music, which could be output. All operating systems allow typically for some sort of input or output. Here's a diagram kind of outlining the general tasks for all operating systems. As I pointed out before, the operating system tends to serve as an intermediary between applications that are needed by the user or through the institution and the actual hardware designed to process that data or input that data or output that data. Now is probably a good time for us to give you a short history of operating systems and operating systems development. Initially, computers were used basically as a large automatic calculator. We used computers to sort out mathematical and statistical problems. As some of you might recall, the very first computer actually goes back thousands of years. This is an abacus. Does an abacus have an operating system? Well, no. Neither does the Zeus, which was built in 1941 by the Germans. And the UNIVAC ran, of course, on transistors and vacuum tubes and took the size of a room. But it really didn't have an operating system. Though legitimate use can be tracked back 100 years or more, there were no practical operating system designs used in significant numbers until the late 1950s. Operating systems of this time were rudimentary, often not able to do more than read punch cards or tape and write output to a machine resembling a typewriter. And it didn't take long before computer applications evolved to do something more useful for a broader audience. Now, computers really didn't see a significant revolutionary development of operating systems until we hit the 60s. And then the computers in the late 60s and early 70s, by today's standards, are quite crude, but they were quite capable. They contributed to the development of space travel, submarine-based ballistic missiles, and even the global financial community. All have something to be owed to the computers of the 60s and 70s. During this time, we also saw some things we take for granted, such as the beginning of the Internet, the creation of input and output devices such as display terminals and magnetic disks, and the creation of more operating systems including OS 8 and Unix. This IBM mainframe, for example, in 1966 used OS 360, one of the first more productive operating systems of the time. In the mid-1960s, we also saw a simple programming language being developed at Dartmouth College. It was called BASIC, or Beginner's All-Purpose Symbolic Instruction Code. Now, prior to BASIC, as I said, programming computers was a very complicated process, and basically scientists and people who did that solely for their existence were the ones who did it. But BASIC allowed non-programmers to start exploring what could be done with computers. In 1975, a man named Bill Gates wrote a compiler, which is basically software that turns computer code written by people into machine code understood by computers. He wrote a compiler for BASIC, and then he sold it to a company called Micro Instrumentation Telemetry Systems, or MITS, and they became the first company to produce an actual desktop computer. Now, this allowed Bill Gates to have enough generate enough money to actually start a company, which he referred to as Microsoft. Now, this led to the development of the Microsoft Disk operating system, which we refer to as MS-DOS in 1980. Yes, I used MS-DOS. It's a text-based program, but it was a runaway success, and it was first widely used and distributed for microcomputers that had to be loaded from a disk or a tape. IBM adopted MS-DOS for its PC and therefore made it more readily available. And in 1984, Apple Macintosh developed the GUI and mouse pointing device. This was revolutionary. It allowed users to interact with the operating system on a graphical screen. That meant you didn't necessarily have to have all the text and text commands to make the operating system work. In 1985, Microsoft released the very first Windows, which provided a GUI interface and many of the same functions as the Mac operating system. So what elements enable an operating system to work with a computer? Well, we have the kernel, which we said before is the basic source code that drives the operating system. We also have something called resource managers, device drivers, application software, and the BIOS. They all work together to ensure the operating system functions. Let's take a look at each of these in more detail, shall we? The kernel consists of the essential program code for the operating system function. Jobs performed by the kernel can include managing the interactions with the CPU, starting, managing, and scheduling programs that handle the input-output activities, including device and networking activities, handling the basic security for the computer, managing the use of computer's memory, which we refer to as RAM, managing priority levels assigned to the programs and to the computer processes. In Windows, the name of the kernel file is ntosKernel, K-R-N-L.exe, and in Mac OS X, we call the kernel XENU or XNU. A resource manager helps us ensure that memory is properly used and that there are no memory conflicts. It also manages how programs access the processing capabilities of the CPU. So an example of which would be if there's one CPU and 10 programs that want to access that CPU, the operating system will give each program a time slice in the CPU and manage that time slice. Each program does a little working during that time slice, and then it has to hand that CPU access back over to the next program. A device driver translates the information necessary for the operating system to communicate with specific hardware. Some hardware that will require a device driver, well, fixed and internal hard disks, mice and trackball devices, printers, scanners, tape drives, flash drives, and other removable media, digital cameras, and video hardware. And there's actually an entire list on page 14 in your book. But for the most part, just about every piece of hardware that you attach to a computer in any way must have some sort of driver associated with it for the operating system to communicate with that device. These drivers will vary depending on the operating system in use by the computer. Here's a diagram that shows how device drivers work. Device drivers interface the operating system with the various hardware devices. They serve basically as a liaison between the operating system itself and the device. Therefore, device drivers are generally written for the operating system. So the same device driver that you run in Windows Server probably will not work for Linux. Any program a user might choose to run on a computer to do the work for that user is generally referred to as an application. Some examples of an application are the word processors, spreadsheets, databases, and even computer games are considered applications. An operating system manages the communication among all these applications, the user and the computer. In this screen, we look at how application programs communicate with hardware through the operating system. As I said before, if you think about each of these applications and programs as different layers, application software generally sits on the top of the layers. The operating system sits between the actual device hardware and the applications and allows the applications to communicate not only with each other, but with the specific hardware devices in use. BIOS also plays an important role in operating systems. The BIOS stands for Basic Input-Output System. It's basically a low-level program code that initiates and enables communications with hardware devices. It's also responsible for performing tests at the startup, which we refer to as the power-on self-test or posting. It also conducts basic hardware and software communications inside the computer, and it starts a full-fledged operating system that will interface with the user. The BIOS is generally the very first thing that starts in the computer when you start it up, and every PC has a BIOS, which is stored in non-volatile random access memory, or NVRAM. Prior to NVRAM, BIOS was generally stored in what we called ROM. ROM stood for read-only memory and could not be overwritten, unlike NVRAM. NVRAM is a memory chip that does not lose its contents when the computer is turned off, however, so that allows it to retain those instructions for each startup process. Now, the NVRAM chip used to store the BIOS, we refer to that as the complementary metal oxide semiconductor, or CMOS memory chip. Now, when we cut on the PC, the way BIOS works, the machine will wake up the CMOS chip and it will begin to run the startup program inside the BIOS. Now, the whole point of this startup program is that it will initialize the screen and keyboard, it will test all the hardware, and then it will initialize the hard drive and other devices. Once it initializes the hard drive, it will load the main operating system onto the hard disk. This is an example of a typical BIOS screen. As you will notice, there are several different options available in this particular boot sequence. The boot time diagnostic screen, whether it will boot in what we call quick boot mode, restore on AC power loss, first boot device, second boot device, and so on. Additionally, in the BIOS, you help set up the hard drive and removable devices. In this diagram, we further extrapolate from the original diagram how the operating system works. Notice that we have all the various components of the operating system included in this diagram to kind of give you a better understanding of how they function within the operating system. Operating systems are organized by the size, type, and purpose of the computer on which they run. For example, the computer in a microwave oven. Well, yes, it too has an operating system. It requires input from the user, and the output is the type of wattage, the length of time that it cooks, etc. But anyways, it needs device drivers for the LED display, the keypad, and even the door close switches. Another example would be a PC class computer designed for individual users to perform tasks. Word processing, spreadsheet management, and networking, to say the least, along with connecting with other computers. Early operating systems were written for large, refrigerator-sized machines, and they were quite complex. Applications were written with efficient code, and the appearance was very basic. However, today, when we talk about big machines, we no longer have to refer to them by the physical size. Big now refers to the processing power and the memory storage for that computer. To operate today's more powerful computers, we need more powerful and more capable operating systems. Today's operating systems must support multitasking, high-speed network applications, and more powerful input-output capabilities. In today's high-end workstations, they quite honestly look very similar to low-end workstations. The difference today is usually the applications in which it runs and the hardware that it has inside a box. Things like the size and speed of the disk controller, the hard disk, the amount of memory, and the size of data pathways, whether it's 32-bit, 64-bit, or higher, or the speed and number of CPUs that are stored. Computers and operating systems can be looked at in terms of one or more of the following characteristics: time sharing, real time, or whether or not they're multi-user. A time-sharing system is a central computer system that is used by multiple users and applications simultaneously. Mainframe computers are a perfect example of a time-sharing system. They're used to perform massive calculations or manipulate large amounts of data, usually in batches. An example of batch processing would be things like clearing 2 million checks and updating their associated bank accounts. We generally do this in batches instead of on a single check-by-check basis. Sequential processing is used by smaller computers where each process request is completed and the data returned before the next process is started. In this diagram, we show a little bit about how time sharing works. Notice that there's a mainframe with different terminals connected to the mainframe. A terminal is basically a dumb computer. It requires the actual mainframe to do the processing power. A real-time system is an operating system that will interact directly with the user and responds immediately or almost immediately with required information. An example of which would be when a scientist calculates the size of an iceberg, and the computer program will immediately perform that calculation and return the answer to the scientist. It uses sequential processing instead of batch processing. That's one of the big differences between time shared and real time. Windows 7 and Mac operating system 10 Snow Leopard are examples of real-time systems. And real-time systems are indeed what most of us are familiar with and work with today. In this diagram, we show how real-time systems interact. It uses typically a network to access a real-time Windows server. Now, the server may or may not process data for the real-time systems, but one thing's for certain: the data that was processed will be processed in a sequential manner. A multi-user system is capable of supporting multiple users who are accessing the computer and the operating system's hardware and software facilities. It's important to note that both time-sharing and real-time systems can have the capability of being a multi-user system. Client-server systems are systems where a small part of the work is done on the central computer, which we refer to as the server, while most of the work is performed on the computer at a user's desk. We refer to that as the client. A lot of applications today rely on the client-server infrastructure model. An example of which would be an electronic health record system, where a doctor on a client system will refer to a patient record, and that record is stored and then delivered by the server to the client for processing. Client-server computing was not possible until the PC was introduced. Another type of computing is cloud computing. It allows us to provide scalable web-based applications and services over the internet that are used by clients through web browsers. Now, Microsoft describes three types of cloud models: the private cloud, where computing resources are kept within an organization and used exclusively by that organization; the hosted private cloud, where resources are made available through a third-party outsourcer, but then they're only accessible to users within a specific organization; and then the public cloud, where a variety of resources are available to any organization through a third party. Each organization subscribes only to the specific resources which may be shared by other organizations. This diagram is an example of cloud computing. Notice that all the different computers are connected through the internet to a wide variety of applications. It's important that we discuss single tasking versus multitasking. First of all, earlier versions of operating systems allowed programs to directly access the hardware. These systems were more prone to unexpected hangs, system instability, or crashes. But today's operating systems manage access to the hardware. The major reason for this was to facilitate multitasking, or running two or more programs at the same time. There are two general types of multitasking: cooperative multitasking and preemptive multitasking. Let's discuss both of these. In cooperative multitasking, the operating system hands over control to a program. It will then wait for that program to hand the control back to the operating system. This is an important differentiation. If the program does not give control back to the operating system, it may hog the CPU until the operations are complete, or it could hang altogether. No other program can run until the control is given back to the operating system. We found cooperative multitasking in earlier versions of Windows. An example would be if you print a word processing file and tried to play solitaire, you would not be able to play a single card until that print job has finished. This is an example of cooperative multitasking basics. In this diagram, we go from point to point, showing that the operating system gives control over to the program. The program then will perform those functions, and then it will return the operating system control of the CPU. Only once the operating system gets control of the CPU can it then delegate program 2 to use the CPU resources. This process goes on and on. In preemptive multitasking, however, the operating system is in control of the computer at all times. It will let programs execute a little bit of the code at a time, and then it will force that program to relinquish control of the CPU. This is referred to as a time slice. The operating system has control over how much of the computer's resources will be allocated to each program, and for how long. It's now found in modern operating systems like Windows XP, Vista, Windows 7, Server 2008, and Mac OS X, and even Linux. You could play solitaire while printing that word processing file we were discussing earlier using preemptive multitasking. Computers must use more of its CPU and memory to support this operating system, but this allows typically for a more stable, reliable operating system. In this diagram, we attempt to show how preemptive multitasking works. The operating system is responsible for the internal tasks, and it will continuously run while other programs are running a few cycles at a time under the control of the operating system. In single tasking versus multitasking, a single tasking operating system is only capable of executing one program at a time. In order to do something else, one program must be stopped. You saw this a lot in older operating systems. MS-DOS, for example, was a single tasking operating system. Now, in a task switching operating system, more than one program can run at a time, but only one program can have control at a time. Earlier versions of Mac operating system were considered task-switching operating systems. In this example, one program and another program are running. However, in this operating system, the user will instruct which program has control over the resources at any given moment. It's important for us to differentiate between single-user operating systems and multi-user operating systems. A single-user operating system can only handle one user at a time, while a multi-user operating system handles multiple users at any given moment. Now, some desktop operating systems are only single-user, while all server operating systems are considered multi-user operating systems, and some desktop operating systems even have limited multi-user capability these days. Some single-user operating systems do not use multitasking, while many of them do use multitasking, but a multi-user operating system will always employ multitasking. A single-user operating system that can use multitasking, it has the ability to use either cooperative or preemptive multitasking in its infrastructure, while a multi-user operating system will always be using a preemptive multitasking strategy for its operating system. Let's look at some of the current operating systems that are covered in this book today. The most common operating systems that we'll cover include Windows XP, Vista, and Windows 7, the desktop operating systems. Windows Server 2003 and Windows Server 2003 R2. You still see this a lot in many server environments, while Windows Server 2008 and Windows Server 2008 R2 are becoming more commonplace. There are many different distributions of Unix and Linux. In this lecture, we'll focus on Fedora and SUSE. And Apple Macintosh, Mac OS X, versions 10.5 Leopard and 10.6 Snow Leopard. In Chapter 2, we're going to talk about these operating systems in more detail. Let's summarize the chapter. An operating system provides the foundation upon which to run the components of a computer and execute applications. A basic task of an operating system is to enable a computer to perform input-output functions. There are two common types of operating systems, desktop and server. The history of operating systems and computers represents a progression from a physically huge computer to large computers to desktop-sized computers that have powerful operating systems. Device drivers can extend the native function of any operating system to provide access and control over different types of devices. These would include printers, DVD, CD-ROM drivers, hard drives, modems, and the like. The BIOS is considered the low-level program code that operates between the computer hardware and the operating system. It's important to have the BIOS to initiate the communication, perform hardware tests, and enable the actual startup of the operating system. An operating system may be geared to run a large mainframe or a small PC type of computer. Operating systems can be understood in terms of characteristics such as time sharing, real-time operation, and multi-user capabilities. From the standpoint of the user, one of the most significant advances in operating systems is the refinement of the GUI in Windows-based and Mac operating systems. Early operating systems tended to be single-tasking, but modern operating systems today are largely multitasking. A true multi-user system is one where multiple users access and run a single application on a single computer at the same time. Some operating systems are multi-user and some are single-user. Currently, popular operating systems are the topic of this book, and these will include Windows XP, Vista 7, Servers 2003, 2008, Unix, Linux, and Mac OS X Leopard and Snow Leopard. That's it for Chapter 1. Please be sure to read over the chapter, and we'll see it when we talk about virtual machines.